All right. In this chapter, we'll talk about waves. Okay? And so here's what they are. So in the last chapter, you talked about simple harmonic oscillators. So here was an example. Okay. So here was a mass attached to a spring. Okay. In an oscillator, what did you need? You needed two kinds of energies. Okay. Two or more kinds of energies. And the energy oscillated from one kind to another. Okay, there were two kinds. So for instance, in this case, energy oscillates from potential to kinetic energy as this thing oscillates. For an oscillator, for a simple harmonic oscillator, what you need is if you disturb the system from its equilibrium position, there needs to be a restoring force, and the restoring force needs to be proportional to the displacement. That's a simple harmonic oscillator. Okay, and like I said, so this is a system that you will that will follow you the rest of your lives if you're an engineer. Okay. So now that you're an expert at this simple harmonic oscillators, what is it that you're going to do? What you're going to do is you're going to take a million of these and make them oscillate together in a choreographed manner. Okay? So as soon as you become an expert at one, then you'll so they're all dancing together. They're all in simple harmonic motion. Okay? And this is what we're going to study. Okay? So each point on the spring is undergoing simple harmonic motion. Okay? And so on. All right, so this is the wave. I mean, you all know what a wave is. So this is a wave, and we'll study this. We'll study the mathematics of this. Okay? Since you guys are all experts at differential equations, what is it that you want to do? Here's your system that you want to study. You want to write a mathematical model for the system. Okay, so we'll introduce you to another differential equation called the wave equation. Okay, that'll be a mathematical model for this system. Okay. So we have gotten to a point where we want to use mathematics to describe everything. English is not good enough for us. Okay. All right, so now let's look at some of the features. Okay. For a wave to propagate in a medium, to create a wave in the medium, what you need to do is pump energy into the medium. So you saw that uniform circular motion was the sum of two harmonic motions, simple harmonic motions. And what this oscillator is doing is it's pumping energy into this medium. Okay, well, you're pumping energy into the medium because you're doing work. It takes force to do this thing. Okay. If the energy was not traveling anywhere, it would collect over here in this location where you're putting energy in there, and before long you would have an explosion. You don't have an explosion, so what can you surmise? That the wave is carrying energy away. So all waves carry energy. You can go outside, it's a beautiful day, in the sunshine, you stand in the sunshine and you'll feel warm. So electromagnetic waves have brought energy from the sun to you 100 million miles. Okay? So all waves carry energy. Okay? There will be a type of wave which doesn't carry energy, but we'll talk about that later. Okay? All right, so waves carry energy. When a wave passes through a medium, it is disturbing the medium. But you see, the medium itself is not transported. That point is going nowhere. All it's doing is oscillating. All right, so here's another demonstration for the fact that waves carry energy. Let's say you have a boat anchored on a lake. You drop a rock a little distance away. You have waves going on the surface of the lake, and they'll rock the boat up and down. And you need energy to lift the boat up and down, okay? Make it oscillate. and that energy is being deposited. It's coming in the waves. Okay. All right, so those are some of the things about a wave. Okay, waves carry energy. There are disturbance in the medium. Okay, these are called mechanical waves. This is a wave that is traveling in a medium. Electromagnetic waves can travel through perfect vacuum. Okay. This is, I'll tell you one more thing about this wave. This is a transverse wave. Okay, you can see that the wave is traveling in this direction, and the particles of the medium are oscillating perpendicular to the direction in which the wave travels. So that is a transverse wave. Sound waves in fluids are longitudinal waves. So a sound wave will travel in that direction, and the particles will oscillate like that, parallel to the direction of travel. So those are longitudinal waves. Okay. All right. So now you have a sense of what waves are. So let's get into the slides. Okay. So we'll talk about waves. Okay. Transverse and longitudinal waves will define some wave parameters. Okay. We told you that all waves carry energy, so we'll give you an expression for that. And this wave equation will be the mathematical model describing the behavior of that system. Okay. And then we'll talk about standing waves. Anybody know where these things come in? Okay, whenever you play any instrument, musical instrument, okay, so you're setting up standing waves. And so we'll talk about that. And we talked about resonance last chapter. What is resonance? Do you guys remember what's resonance? So resonance, again, is every system has a natural frequency of oscillation. And if you force it at its natural frequency, and if you're putting in more energy than is being bled away every cycle, then you can set up large amplitude oscillations. Okay? And you can break bridges, you can break wine glasses, and all kinds of stuff. Okay? All right. So we'll talk about types of wave. Mechanical waves are waves that need a medium to travel in. Electromagnetic waves can travel through vacuum. Yeah. All these guys are electromagnetic waves, lights, radio wave, X-rays, and stuff like that. Matter waves, okay. So particles have a wave nature to them. Now those don't carry energy, those are probability waves, okay. And the wavelength is given by this. So you guys have heard of electron microscopes, and that's how this is. Okay. So here's a simplistic view, but okay. So for a wave, so here's a wave. So here's this wave. This distance is called the wavelength. Okay. So crest to crest distance is called the wavelength. All right. So if you're looking at something, so how do I see you guys? What is happening? How do I see you guys? So light is reflecting off of you, and I'm detecting that light. Okay. Now, if I use a light of wavelength that, the question is, what is the smallest thing I can see with that light? It turns out that the smallest thing I can see is the size of the wavelength, roughly. Okay? So, for instance, visible light that our sensors, we have sensors. You have two sensors for electromagnetic waves. Well, you have more than two sensors, but these are the best ones. These guys see from 400 to 700 nanometers, your eyes. Okay? So if you're using light, Then the smallest object you can see is 400 nanometers. Okay. The size of an atom is about 1/10 of a nanometer. So 400 nanometers is roughly 4,000 atoms. So using visible light, the smallest object you can see is roughly 4,000 atoms. Yeah, I'm giving you ballpark numbers. What if you want to see something smaller? What if you want to see a single atom? You can't use visible light. Okay. It turns out then that X-rays, the wavelength of X-rays are close to the wavelength of a single atom, the size of a single atom. So you would use X-rays. What if you want to look inside an atom? X-rays are not good. All right, so it turns out that if you have electrons, these moving electrons, moving particles, all particles, they have a wavelength associated with them. The wavelength associated with them is h divided by their momentum, mass times velocity. All right, so you see, the faster a particle is moving, the smaller its wavelength. So all you have to do is just use the right speed electron. You have a wavelength small enough for whatever it is that you're looking. Now, most massive particles, my wavelength when I'm walking, my wavelength is so tiny that that's not useful. Okay. So electrons, you can use electrons in electron microscopes. Okay. All right. Okay, so general features of a wave. When a wave travels through a medium, matter is not transported, only the disturbance travels. All waves carry energy. Okay. What are transverse waves? We just learned that if a wave is traveling in this direction and the particles oscillate like that, those are transverse waves. Okay. A longitudinal wave is if a wave travels in this direction, particles are oscillating parallel to the direction of wave travel. In a transverse wave, particles are oscillating perpendicular to the direction of wave travel. Yep. There are other kinds of waves, complex waves. Water waves turn in, so if you go to the beach here and you see a wave coming at you, those water molecules on the surface are going in a circle. So they are a combination of a transverse wave and a longitudinal wave. Okay. All right, so let me show you some okay. So here's a sound wave. To make a sound wave, all you have to have is some diaphragm or surface, and you make it oscillate. And this thing is pumping energy into the air, and you see this wave is traveling in that direction. Okay, so a sound wave in air is a pressure wave in a fluid, in solids, and stuff like that. In solids, you can have transverse and longitudinal sound waves. In a fluid, in gases and liquids, you can have only longitudinal sound waves. Okay. Okay, so you can see that this is a high pressure area, and in between you have low pressure. So it's a pressure wave, and it's traveling in that direction. And you can see, if you could see each molecule, that's oscillating parallel to the direction of travel, that red dot. Okay. You guys can see that red dot, right? Okay, so this is a longitudinal wave, and here's a transverse wave. So in a transverse wave, there's the wave traveling and particles are oscillating back and forth. This is not that good one, but anyway, that's what that is. Okay, so that's a transverse wave. So in a only in solids can you have transverse waves. Liquids, fluids do not support transverse waves. All right, so now we'll look at some wave parameters. One of the important parameters is the wavelength. Wavelength is crest to crest distance. The amplitude, so for instance, the color of light is related to the wavelength. Okay. Amplitude is the maximum displacement from the equilibrium position, and that's related to the intensity of sound. So if sound gets louder, that means its amplitude is higher. Okay. And you'll see that a wave carries, the energy a wave carries is proportional to the amplitude square. So if you double the amplitude, the power carried, energy carried per second quadruples. Okay. The period is the time for one oscillation. It's the time for one oscillation. It also is, if you stand here, that's the time it takes for one wave to pass you. Okay? So those two times are the same. You can think of it either as one oscillation or the time for one wavelength to pass you. Frequency is how many oscillations do you get per second. Or if you're standing there, that's how many waves will pass you in a second. Okay? So if the frequency is 10 hertz, that means 10 wavelengths will pass you in 1 second. Okay? And frequency and period are related like that. Frequency is inversely related to the period. Of course, we want to describe everything mathematically, so we are going to, these two parameters will be convenient in the mathematical description. This is called the wave number. It's 2 pi divided by the wavelength of the wave. Okay. And omega, the angular frequency, is 2 pi times the linear frequency. Okay. And the linear frequency was 1 over t. Okay. So these two parameters will be useful in mathematically describing this wave. So for instance, we want to describe this guy mathematically. Okay. And we'll show you how to do that. Okay. All right, so let's say here is a function. Okay, so here's a function like that. And what if I want to, okay, so let me do this. So you guys know this kind of stuff from your math, from your calculus classes. I'm just sort of reminding you of this. So let's say you have a function like this, f of x. Okay, what if I want to shift this function, move this function to the right? I want to slide it to the right by a distance b. How do I do that? As soon as I tell you, it'll spring to mind. Okay, so this is f of x minus b. X minus b. Okay. So I'll show you something neat. If you want to shift it to the left, it's f plus x plus b. Okay. So that would be fx plus b. F x plus b would shift it to the right. Now think about this. So instead of this, now I want to get a little more ambitious. I just don't want to shift it. What I want to do is have it move at a velocity v. Okay, now I want this wave to travel to the right at velocity v. How do I do that? Uh-huh. Yes, so if it's traveling with velocity v, after 1 second, how far has it traveled? V times v. After 2 seconds, it's traveled 2v. After 3, okay, so it's just x minus vt. Okay, so that travels to the right at velocity v. Okay, after 1 second, it's 1t, 1v. After 2 seconds, it's 2v, and so on. So there you go. Okay, so that little trick showed you how to make a wave travel to the right. Okay. So you already learned this trick. So there you go. This is a wave traveling to the right. Okay. And you just make it travel. You learned how to make this function travel to the right. Okay, so let's do that. All right, so let me draw a sine function. Okay, sine x. Okay, and now I want it to travel, this function to travel to the right at velocity v. Okay, so this function will go to sine x minus vt. There you go. You have the function traveling to the right. Okay. Now, what is the wavelength of this wave? It is 2 pi. Okay. What if I want to make a different wavelength? What if I want this wavelength to be lambda? So all I do is change that function sine 2 pi by lambda times x. See, now this sine function, when x equal to lambda, then it'll be 2 pi, and so this function has a wavelength of lambda. Okay, so that function, so if this wavelength is lambda, okay, and this amplitude is 1, this is sine 2 pi x over lambda. This was the wave number. That's why we defined the wave number k. Okay. So this was equal to sine kx. All right. Now you want this to travel to the right. So all you do is replace kx by x minus vt. So here is your wave, a sine wave of wavelength lambda traveling to the right. Okay, and if you want to change the amplitude to A, you just write A. Okay, so here is a sine wave of amplitude A traveling to the right at velocity v. All right. So, and in a second you'll learn that velocity can be written as the velocity of all waves is frequency times the wavelength, okay? And it can be written as omega over k. So your function, wave function x of t is sine k x minus vt. Okay, equal to A sine k x. V is omega over k t. This is equal to A sine kx, k times x kx, and this k cancels, so it's minus omega t. So what you have learned is, what is this guy? It's a sine wave traveling to the right. With velocity v. Okay, so here's a wave there, that's the amplitude. The amplitude is related to the intensity of the sound. This is the wave number, which is related to the wavelength of the wave. Omega is related to the frequency of the wave, okay? And this is the wave traveling to the right. And velocity of the wave is omega by k. So now you learned in 2 seconds, in 30 seconds, you've learned to mathematically describe this fella, okay? That looked pretty complicated, but now you know how to do it. What if I wanted to do a wave traveling to the left? What? Yeah, it would be kx plus omega t, okay? All right. All right, so there you go. There's your wave traveling to the right, okay? K is called the wave number, omega is the angular frequency, A is the amplitude, okay? So here's a function that's a function of both x and t, okay? That means, what that means is, see, for a given time, if you take a photograph for a given time, you see y is this displacement, y is changing with x. And then if you let time flow, you'll see that at each location, y is changing with time. Okay, so that's what this function tells you. Okay. All right. Each element of the string moves up and down in simple harmonic motion. So each element of the string is moving up and down like that mass attached to the spring. It's a simple harmonic motion, okay? Remember, so last chapter you learned about simple harmonic motion, and now you're combining billions of simple harmonic motions. All right, to get the wave velocity from here, the wave velocity is, you mark this point on the string and you follow it, okay? You find out at what speed is that guy traveling, and that's the wave velocity. Okay. And so it turns out that this guy is called the phase of the wave. Okay, so this term is called the phase of the wave. So when you're tracking this point, what you're tracking is the point of constant phase. This point has a given phase, and how is that phase traveling, okay? So there's the phase, that's the constant, okay? And what you do is, so all you do is take the time derivative of that. K is constant, dx by dt, so that tells you the rate at which that point is traveling, okay? Minus omega t and equal to 0. So dx by dt is the wave velocity, and that's equal to omega by k. And that's equal to frequency times lambda. Omega by k. Omega was defined as 2 pi over times f, and k was 2 pi over lambda. So that's the velocity of all waves. Okay? What is this guy? Is it a traveling wave or a wave at rest?
Traveling to the left.
Yeah, traveling to the left. That positive sign tells you traveling to the left. Okay? And here's how you remember it. See, remember the wave travels in the direction where this phase is constant. If t is increasing, you have to reduce x to keep this constant. Okay? And so the wave has to travel to the left. Okay? So that's how you figure out which way the wave is traveling. Okay, that's one way to figure out, or you can just remember it. You want to keep this constant. That'll tell you the direction of the travel. If t is increasing, x has to increase to keep that phase constant. So the wave is traveling to the right. Okay. All right. So what have we done? We have learned how to describe a sinusoidal wave. Okay, a wavelength lambda, amplitude a. Okay, and so the traveling wave is given by, here's the amplitude of the wave. It's a sine wave. K is the wave number. X plus or minus omega t. The plus tells you it's traveling to the left. Minus tells you the wave is traveling to the right. So that's what you have learned so far. Okay. All right, let's go back to our simulation. Okay, so now watch what will happen. What I'm going to do is I'm going to reduce the, okay, so you guys have all experienced this. You take a string and then you can send a wave down a string. Can you do that down spaghetti? Let's say a cooked spaghetti. Can you send a wave down a cooked spaghetti? So no, right? If the tension decreases, the wave travels slower. Okay, you have to have tension in the string. So watch this. I'm going to reduce the tension in the string. So we need to give it a second to settle down. Okay, so it turns out that the speed of the wave depends on the tension. The more tension there is in the string, the faster wave will travel. Okay. I guess it's hard to see that in there. Okay, so the speed of the wave in this on a string depends on the tension and the mass per unit length. Mu is the mass per unit length of this on the string. Okay. So for instance, you might have experienced this if you play a guitar. If you tighten the strings, what will happen to the frequency? The frequency increases. Okay, so velocity is frequency times wavelength. When you tighten the strings, see the wavelength is dependent on the length of the string. You're not changing the length of the string. All you're increasing is the tension, and as the velocity increases, the frequency increases. Okay. So the velocity of a wave on a string is square root of tension in the string divided by mass per unit length. Okay. Okay, so when a wave travels on a string, you see this was the unstretched position of the string when there was no wave. And you see when a wave is traveling, see the string is stretched. So it's like a rubber band. When you stretch a rubber band, what have you done in it? What kind of energy is stored in the rubber band? I'm sorry? Potential energy, elastic potential energy. Okay? So you see there's elastic potential energy in there. And then also each piece is oscillating like that. It has kinetic energy. So this wave traveling on the string has both potential energy and kinetic energy. Now, it's slightly different than the oscillator, but I mean in a different sense. Okay. Here, for a mass attached to the spring, I don't want to confuse you, but anyway. So here's a mass attached to the spring that's oscillating. For a mass attached to the spring, this point has the maximum kinetic energy and this point has the maximum potential energy. Okay. For this string, this element is unstretched, so it's got minimum potential energy and it's at rest, so it has minimum kinetic energy. This point is moving the fastest and it is stretched the most, so this point has maximum potential energy and kinetic energy. Okay. It's under tension, the force on this point is 0, the force on this point is the maximum. Okay. Anyway, what I want you to remember is that there's potential energy stored in the string because it's stretched, and then there's kinetic energy in each element. Okay. So as the wave travels, the relevant question is, okay, I'm going to stand here and I want to know how much energy is passing me every second. Okay. So that's the question. Okay. And that is given by the power transmitted. Okay. So if you're standing here, the energy crossing you per second is given by this expression. And here is the important thing you want to notice. The power is dependent on the frequency square. This is the angular frequency square and the amplitude square. Okay. So if you want to hear something louder, more energy needs to reach you. Okay. So the power is proportional to the amplitude square and the frequency square. And this is a general feature for most waves. Okay. The dependence of the average power on square of the amplitude and frequency is a general result, and it's true for waves of all types. Okay. Okay. This one we're not going to derive. So here's a dynamical system. What do we mean by that? Here's a system that's evolving with time. Okay. And we want to describe this mathematically. Okay. And so we'll introduce something, a partial differential equation to you guys. Okay. So what is happening? See, if you are, see this function, okay, if I freeze it, this function is changing with x, right? Y, that is changing with x, and it's also changing with time. If you're at a given location, that's changing with time. Okay. So y is changing with x, and if you stand at a given location, it's changing with time as well. Looks pretty complicated. Okay. And it turns out that, the two are related. So this is the wave equation. Okay, so here is y that's changing with x, and if you let this film develop over time, then you'll find that this y changes with x. So what this equation is saying is, see, it's relating the partial derivative of y. So this is the partial, and you guys, everybody know what partial derivatives are? So yes, no? We did an example of this. Okay, so let's say you have a function of, I'm just going to, oops. Okay. X, Y, Z. So this is a scalar function. You can put in X, Y, and Z and you can get a number. It'll spit out a number at every location, right? All right. So let's do the mechanics first. Partial derivative of f with respect to x means you take the derivative with respect to x and treat the other variables as constant. Okay. So what is the partial derivative? Del f by del x. Y cubed z to the power 4. So how did you get the partial derivative? You just took the derivative of this variable. You kept y and z constant. Okay? And you can calculate this partial derivative at any location. So now let's look at it physically. Okay, so here is, let's say you're evaluating in that point. And how do you keep y and z constant? If you travel parallel to the x-axis, on this line, y and z are constant. That's what the partial derivative means. How is f changing as you travel parallel to the x-axis? Okay, so that's what that is. How about, I have trouble with this one. Who wants to help me with this guy? Anybody? What is del? Yeah? Yep. Okay. Simple rule. Okay. If you're taking derivative with respect to y, it means you're keeping the other two constant. Okay. So what is this telling you? It's telling you how f is changing as you move parallel to the y. Okay. When you move parallel to y, you're keeping x and z constant. Okay. And we'll give the easy one to Tatiana. No? All right. 4? Oh, there you go. Okay. All right, so that's how we take partial derivatives. And what is that telling you? It tells you how f changes when you move parallel to z. That's what partial derivatives tell you. Okay. All right, so here's a partial differential equation. Okay, y is a function of x and t, and here's the neat thing about this differential equation. You see, it's relating how y changes with the spatial coordinate, and it's relating this to how y changes with the time coordinate. Yep. Mm-hmm.
What does it mean for a wave to be one-dimensional?
Oh, this is traveling only in one dimension. When you drop a rock on the surface of a lake, that's a two-dimensional wave. When I'm talking, this wave is traveling in 3 dimensions. So in one dimension, if there is no friction, the amplitude doesn't change with distance if there is no friction. Okay? In 2 dimensions, the amplitude, that energy is spread over 2 pi r. It's spread over the circumference. So the amplitude, even if there is no friction, will die as 1 over r. In 3 dimensions, it dies as 1 over r squared. So if a birdie is singing here, you listen to a certain intensity. If you're twice as far, the intensity is fallen by a factor of 4. All right, so 1D wave is a wave traveling on a string, okay, for us. Okay, so there's the wave equation. So this is another wave that you will see as an engineer all the time. Okay. Okay, here, yeah.
Why would be the second partial derivative? Because isn't the second derivative of a position function acceleration?
Yeah, so this is the acceleration of this point. That's the acceleration of this guy. Okay. And so here's another thing. Okay, when you're taking a derivative, see, you divided this guy by x. That's a distance. When you took the second derivative, you've divided it by x squared. So you see, this velocity had to be there. Velocity times time is distance, and velocity squared times time squared is distance squared. Okay, so dimensionally, that's you needed the velocity squared. Okay. And that tells you the velocity at the wave at the velocity with which the wave travels. Okay. And so this is a wave equation. What is this guy? What is this guy? It's a sine wave traveling to the right. It's a wave. So it should satisfy this differential equation. It should be a solution of that differential equation. Let's check and see. Okay? Maybe I'm lying to you. Okay? So here is your wave equation. Okay, we'll run. We just told you that this was a sine wave traveling to the right. I'll do it a little fast. Okay. Okay, take the partial derivative of this with respect to x. When you're taking a partial derivative with respect to one variable, what are you doing to the other variable? I'm sorry? Yeah, leaving it be, treating them as constant. So when we take the partial derivative of y with respect to x, we think of t as some kind of constant. Okay? So del y by del x is derivative of sine is cosine, okay? And then we have to use the chain rule, so you get a k a cosine kx minus omega t, okay? Del square, the second derivative would be, what is the derivative of cosine? I'm sorry? Negative sine, and then you'll get another k, okay? So that's minus k square a sine kx minus omega t. Okay. Let's do del y by del t. Okay. Now you're keeping x constant. Okay. So derivative of sine is cosine. And except that you get a minus omega, so it's minus omega a cosine kx minus omega t. Del square y by del t square. Derivative of cosine is minus sine, and then you get a minus omega, so minus, that makes it a plus, so minus omega square a sine kx minus omega t. All right, so let's equate this and 1 over v squared times that. Okay, so is this true? Minus k square a sine kx. So all right, what we are trying to verify is del square y by del x square equal to 1 over v square del square y over del t square. So does our solution satisfy this equation? This guy is there. Oh, wow. When I do that, it can change stuff on another page. That's interesting. Okay, so del square y by del x square is that. We're going to put that here. Minus k square a sine kx minus omega t. That was that. Is this equal to 1 over v square del square y by del t square? Is this guy. minus omega square A sine kx minus omega t. Okay, we'll cancel this fellow, that fellow. Okay, and we'll cancel the minus signs. So our solution would be that if k square equal to 1 over v square omega square. But what was v? V was the velocity of the wave, which was omega by k. 1 over omega square by k square times. So indeed, this guy is a solution to the wave equation. Okay. All right. Question? Okay. Understand? Okay. All right, so we introduced the wave equation to you, and we also gave you the solution without really telling you that, but so that was the wave equation. Okay. Now, so that was a wave traveling. So let me mess this thing up. Okay. So what did that differential equation tell you? It told you how this thing evolves dynamically. Okay. Now I'm just going to mess the whole thing up. Is this motion is obeying that differential equation? Anything you do to the string, that motion satisfies that differential equation. Okay, so this guy is a combination. You guys have heard of Fourier transform? This wave is a combination of several of those simple sine waves. Okay, and that's, if you get the right combination, then it sounds like music, and if you don't get the right combination, it's me on the piano. Okay, so. All right. Okay, now that you know about waves, what we're going to do is all of us are going to talk at the same time. Okay? And we want to find out what somebody hears. Okay? So we want several waves to interfere. Okay? All right, so we'll start with the simplest thing. Here's a string, and we'll send a pulse on the string from the left to right, and send a pulse from the right to left here. Okay, and here's something I want you to notice. Okay, when the two pulses are at the same location, you see they added up. This plus this is that amplitude. But look at this. What do you notice here? So here's the very neat part. So after they've interacted and they go past each other, you see these guys are unchanged. Okay? So these guys are unchanged. And that's not like people, you talk and we change each other. It's not like. So, I say something to you and you go home all mad. Here, these guys, after their interaction, they haven't changed. Okay. All right. When this resultant wave, when they're at the same location, is bigger than either one of them, that's a constructive interference. And if one of them was a negative, so this is constructive interference. We'll come back to this. When two waves like this combine, two waves of opposite sign combine, you see the resultant wave is smaller than the biggest one. That's a destructive interference. And if these amplitudes were exactly equal to each other, they would completely cancel each other. All right, so for instance, let's say I have two speakers, and here's a seat. Okay, so this particular wave reaches that seat with a crest, and every time a crest comes from this speaker, a trough reaches with this speaker, what will happen? They'll cancel. These two waves will cancel. Every time a crest reaches, a trough is reaching. So this frequency you can't hear at that seat. So what do? You charge $1,000 for that seat, okay? And everybody will be mad at you. Okay, so this is destructive interference for this. Okay. All right, let me. Okay, so here's two sources. You can think of them as two speakers. And you see, along those lines, that frequency is completely canceling. Along these guys, those frequencies are adding up. Okay. So that's why there are no seats along the central line. If you have two speakers in this hall, and along those central line, okay, and if the speakers are in phase, every frequency will cancel. So that kind of stuff goes into designing the seating arrangements and stuff like that. Okay. So this is destructive interference, that's constructive interference. And if you guys remember, that's what interferometers used in detection of the gravitational waves. We talked about that. Oh, all right. Okay, so interference is the phenomenon of multiple waves interacting, okay? And at a given location, when they reach a given location, you just take the algebraic sum of them, okay? Constructive interference occurs when the amplitude of the resultant wave is greater than either of the individual pulses. So when they have the same sign, when they interact at a given location, see, the resultant pulse is bigger than either one of them. That's constructive interference. Destructive interference occurs when you have waves of opposite signs interacting, okay? And when they're at the same location, you see the resultant is smaller than the larger one, okay? So this is smaller. Okay, so let's say we send two waves and they cancel exactly. So this is a pure tone you're sending, and they cancel exactly at where Tatiana is. So how do we tell if there was no sound or there was cancellation? The effect is the same on her. You guys understand the question? Okay, so here's how, all she does is moves to a new location. If there is sound, yep. So. All right. So here, this is what happens in musical instruments. So you pluck a guitar string, a wave will travel down the string, it gets reflected at the fret, and then you have a reflected wave. So what we want to study is what happens when identical waves travel in opposite direction in a medium. Okay? We'll first look at what happens when identical waves travel in the same direction. Okay? So here are two waves traveling to the right, the minus sign tells you, and this is a phase shift. Okay? So here are two waves traveling to the right. Okay? And when the phase shift is 0, then it's this, they're identical in the sense that the peaks coincide, and so you get a wave of twice the amplitude. Okay. If the phase shift, if this phase shift, if a trough coincides with the crest of one, then they cancel exactly. Okay. And so these are waves traveling in the same direction. And if there's other phase shifts, then you get a resultant wave. Okay? So these are waves traveling in the same direction. Okay. And of course, you've had trigonometry, and you can add sine and cosine functions. And this is a simple calculation, but it's still a little messy. What if I gave you 3 and 4 waves traveling together? Then it'll get super messy. But we'll show you a little trick on how to add them. But again, that's sort of an esoteric. I mean, we don't concern ourselves with it too much. Okay. So when the phase difference is pi, when this is pi, what that means is the crest of one is coinciding with the trough of another, and when they travel together, they interfere destructively. Okay, they add up to 0. So these are two waves traveling on a string in the same direction. Okay. We won't be interested in that too much. What we'll be interested in is waves traveling in the opposite direction. Okay. But here's that little trick. If you have multiple waves traveling like this in the same direction, okay, when you want to add several waves, you use this trick called phasors. Okay. Does this look familiar? Okay. So if you have a vector A, what is the y component of that vector? Anybody remember? AY is A sine theta. Okay? And the x component is A cosine theta. Look at this. A, let's say that's the amplitude of the vector. And if this was the angle theta, okay, so this is giving you the y component of the vector. Okay, what is happening as time increases? Okay, as time increases, this angle is decreasing, so this vector is rotating like that, clockwise. Okay, so we say there's the phasor, there's the amplitude, and as time increases, it's rotating at an angular speed of omega. Okay, when you want to combine two vectors with phase difference of phi, there's this vector. So you're combining this vector with the phase difference of phi. Okay. There's the phase difference plus phi. You combine this and this, you add these two vectors, and there's your resultant vector. And that's combining like that. And the instantaneous value is just the y component of that, which is that. So the amplitude y prime is related to this vector and that vector and this angle phi. So instead of having to do trigonometric summation, all you do is draw all these vectors and get the amplitude from this diagram. Okay? So this is the phasor. Again, this is not very important. This is, let's say you become an acoustics engineer or stuff like that, or you get into signal processing, then you'll need to know that kind of stuff. Okay, now we want to learn how waves reflect. Okay. So for instance, if you're in a big hall, you get a sound like this, and then if the walls were concrete, you would get an echo from the reflection, and that can mess up the quality of the sound. Okay. Concrete walls reflect quite well. So if you don't want that echo, what is it that you would do? What's that? Yeah. So yeah, that's exactly what you do. Okay. So you put material, cover the wall with material that absorbs sun. Yeah. All right, so you want to learn reflective properties and so on, and okay. Okay, so here you sent down a pulse on this string, and then when it reflects, you see a positive pulse became a negative pulse. Okay, when it reflects off a fixed end. Okay. And this is not just academic. For instance, if light hits my glass and reflects off of my glass, this is what's happening. Okay, so it's fixed end reflection. If light hits a medium whose refractive index is higher, that is like this, and it reflects, the amplitude changes sign. If the end is free, you see this pulse going there. When it gets reflected, it still remains positive pulse. Okay. So this simulates light going from air to glass. So when it hits there, it will become of opposite sign, and this reflects light traveling from glass to air. Okay. When it reflects of this medium, it doesn't change sign. Okay. So that's the kind of stuff. That's why we want to know how the reflection properties, and I'll show you a okay, so you can see that. Oops. Okay, there we go. So when pulse reflects off a fixed end, the amplitude changes sign, and when it reflects off of an open end, it doesn't change sign. Okay. All right. So you guys can see my glasses are anti-reflective. Okay. So what is happening? You pay a little extra for this, so you can see my eye. What is happening here is, what they do is they charge you a little money. So here's my lens. I'm just going to draw a lens like this. Okay. And they will put a small plastic coating on this lens, and they'll charge you $30 for it or whatever. Okay. And what does this guy do? Okay, so this light reflects off of there, and when it's reflecting, this is a closed end reflection when it comes from air to this plastic. Okay. And closed end reflection, that reflected light goes like that. It switches amplitude. Okay. There's another beam that goes through here. It goes through here and it reflects off this end. That is going from from plastic to, okay, so it depends on the refractive index of this medium and this medium. If the refractive index of this medium is greater than this medium, then it will, if the refractive index of this medium is less than this medium, it would reflect just like that. Okay, so we'll assume it's that, because, and this also gets a negative sign and then comes up. But what you're doing is, the thickness of this medium is such that this beam, when a crest comes, for this beam, because it traveled this extra distance, this beam is coming out with a trough. And so this beam, when it reflected off, if this thickness was not right, if you get this beam reflected, then you get a glare and you can't see my eye. That glare is messing up the light coming from my eye. Okay, so when they put this thickness of plastic, the right thickness, this glare is cut off and then you can see my eye. Okay. So these are anti-reflective coating, and so this is the kind of stuff that all this information is useful for. You guys have seen those cars that go by, and as they're going by, their colors change? I'm sorry? Okay, so how's that happening? It's not, they don't have different colors. What they are same thing like this nowadays. So that product is possible. This is the car. And they have technology where they can place an even thickness clear plastic on it. Yep. So here's a car. And there's the even thickness plastic that they put. And so at this angle, red light is canceling, but blue light is not canceling. And you can see it blue. At different angles, different colors cancel. And you can, so at this angle, red light is canceling and green light is not. Okay? And so, all right. Now we'll talk about standing waves. Okay, so standing waves are what you set up in instruments, okay, in musical instruments. Okay, so on a guitar string, when you pluck a guitar string, you'll send a wave like this down a string. It reflects off the fret and then comes back. So you have two identical waves traveling in opposite directions. Okay? And here's a wave traveling to the right. Here's a wave traveling to the left. Their amplitudes are the same. Their wavelengths are the same and the frequencies are the same. So you have two identical waves traveling in opposite direction. And if you combine the two, look what happened. What is this? Okay, for a wave to travel, you need x minus t. X minus vt. Okay, so there needs to be a difference in these coordinates, the spatial coordinates. See, there's no difference there. See, this is a sine wave that's at rest. And here's the time part that is separated. That's just making it oscillate. This is not a traveling wave. This is a standing wave. Okay? This is a traveling wave. This is a traveling wave. So let me show this to you on a simulation. Okay, so this is just adding two waves. Okay, here's adding one wave that is stationary and one wave that is traveling, and that's what this wave is. So sine waves traveling in opposite directions create a standing wave. Okay, so what we'll do is, so here's a wave traveling to the right, and here's a wave traveling to the left. And let's see, when you combine the two, what happens. There's that resultant wave. So on a guitar string, you set up one wave traveling to the right, it reflects off the fret. Here's a reflected wave, and they combine, and you see this is the standing wave. This wave is not traveling in, so the string is oscillating like that. Okay? So in all musical instruments, you set up standing waves. When you play a flute, the sound wave travels down the flute and reflects off the end, and the air in it is a standing wave. It's oscillating in a standing wave pattern. Okay. So this time-dependent phase factor does not have a spatial part. This is a standing wave. So the spatial part and the time part are separated. Okay. So here's a guitar string. Like I said, you can only set up standing waves on a guitar string. And here's the lowest frequency of oscillation. Okay. So, and this, so on the ends are not vibrating, so those are called nodes. And the spots where you have maximum vibration, those are called antinodes. So this string, this length string, can only oscillate. So the lowest frequency it can oscillate is that frequency. This is the next higher mode. And you see this wavelength, so there's the wavelength. The wavelength for this is twice the length of the string. So the wavelength is half this wavelength, the frequency is twice this frequency. So if this was F, the fundamental frequency, this is 2F1. This is 3F1. So this is a harmonic series, okay? Integer multiples of the lowest frequency. So string fixed at both ends, the frequencies of oscillation are integer multiples of the lowest frequency. Okay? So the allowed frequencies are integer multiples of the lowest frequency. Okay, so and this is the lowest wavelength, and so it's integer multiples of that. Okay. Velocity is tension divided by mu. So n, this is n equal to 1, n equal to 2, n equal to 3. Okay. L is the length of the string. Tension divided by the mass per unit length. Okay. So what I'm telling you is, for this length, this string can only vibrate with certain frequencies. This is 50 hertz, 100 hertz, 150, and so on. Okay. So how do you play music with an instrument like guitar? You're producing all kinds of frequencies. So what is it that you're doing? How can you produce all kinds of frequencies? Yep. That's right. So when you press down on the fret, you're changing the length. The smaller the length that is vibrating, the higher the frequency. So you have that under your control. The tension, you can't change the tension while you're playing. That you set up at the beginning. What else can you do? You have 6 strings at your disposal. You can pick one of 6 strings. They all have different weights. The heavier string produces lower frequencies. Okay. So those 2 parameters are under your control. The length of each string and the weight of the string that you choose to pluck. Okay, so that's how you produce music. All right, so here's for a string, higher frequencies are integer multiples of the fundamental frequencies. So higher frequencies are integer multiples of the fundamental frequencies. Look at this. Here's a drum head. Okay. So, and I'll show you how a drum head vibrates. Okay. And the second higher frequency is not an integer multiple of the lowest frequency. It's 1.59 times the lowest frequency. So these are not, see all these higher frequencies, they're not integer multiples of the lowest frequency. Okay, so they don't form a harmonic series. Okay. So let's look at how a drum head vibrates. Can you see that? So that's the lowest mode of vibration of a drum head. Okay. No music. There's the second higher mode. So when you pay for drum lessons, you're learning how to hit on different spots on the drum head to excite all different kinds of frequencies. Yep. So here's a famous problem. Okay. So the question was, can you, from the music that you hear, can you tell the shape of the drum? Okay. So, and the way you solve this problem is you find out what are the frequencies at which it can vibrate. So these are eigen frequencies if you want. Okay. These are the eigen frequencies of the drum head. And it turns out that Mark Gack, he was a very famous mathematician. Anyway, eventually it was solved. It turns out that, you see, these two drum heads produce the same frequencies. You can't tell which drum head it is. Okay. And so it turns out what is true of these two drum heads is their area is the same and their perimeter is the same. So the area and the perimeter of those two shapes is the same. They produce the same frequencies. Okay, and you can't tell if you can't tell from listening to those being played if which one is which. Okay. You can tell the difference between this drum and that drum. Okay. So anyway. So this is a pretty famous problem.